So this homework question was essentially saying, which one of these scenarios, or which of these scenarios would light the light bulb up? So we have a wire, and in a couple, actually in all of these this wire here has a current flowing through it. So what's the first rule that we discussed? We have a current flowing through a wire, what happens? So there's Kirchhoff's law that all the junctions have to, the current into and out of all the junctions has to be added to zero, and any loops of wire, the voltage drops and voltage increases around that have to be zero. But here I'm just assuming that all the current is coming into this node and out of this node. So essentially we just have current flowing through this wire. What else about current flowing through a wire? What else do we know about that?
You lose heat or you lose resistance through heat.
It's another true thing, not what I was looking for, but true. So if this wire has some resistance, how much heat, so let's say this wire has resistance R, and we have current I flowing through it. How much energy is getting converted to heat? So there's two main rules. You don't need to have them memorized. You can put them on your cheat sheet. But two main equations are P equals VI and V equals IR. So should have, they're easy enough that you should have them memorized. But of course, you'd want to write them down in your cheat sheet regardless. So I said, what is the power being lost, or how much heat power is being produced by this wire with resistance R and current flowing through it I? How can I figure that out? Actually, how can I calculate power knowing only V and I'm sorry, knowing only I and R? Can I? Is there enough information there?
P equals I squared R.
Yep. So if I just say P equals IR times I, so I put in the equation for V there, and so I get I squared R. So if I double the current in this wire, what do I do to the heat losses? They're quadrupled. So because it's I squared R. So we actually, if we're trying to minimize losses, we try to minimize current, because if we cut the current in half, then we cut losses by 4. How can we transfer the same amount of power through this wire if we lower the current?
Decrease the resistance.
I'm sorry, how can we transmit the same amount of energy through the wire? Not the energy that's being lost to heat, but so we have some energy that's being lost to heat, which we're trying to minimize, but we're trying to send the same amount of electrons energy through this wire. So if we reduce the current, trying to minimize the I squared R losses in this wire, how can we have the same amount of energy leaving? Increase. No, so that's awesome. So increasing the resistance would increase the losses, not, so do we notice, so we see the difference? Let's say we have so if this is the resistance of the wire, and this is essentially the resistance of the load. So how do I make, essentially, if I want the same amount of power to come out of this load, let's say that this is a light bulb, and the amount of power that light bulb consumes is a function of its resistance and the current flowing through it, I squared R. This is the thing that we want to consume energy. This is the thing that we don't want to consume energy. So if we can't control this resistance, what we could do is we could try to decrease the amount of current that's going through here and increase the voltage. So that's, once again, in the side. So coming back to this problem, where your answers, let's look for something that has to do with both electricity and magnetism. So we have current flowing through a wire.
Creates a magnetic field.
Creates a magnetic field. Current flowing through a wire creates a magnetic field. Okay, so now I have a coil of wire up here. What did I say about a magnetic field and a coil of wire? The third rule.
It produces a flux in the magnetic field.
So the magnetic field has a flux going through this.
But only this way.
Well, so the magnetic field, so this this wire has a magnetic field that goes around it, kind of like this.
I don't really know how to visualize the magnetic field. Like, are we using Earth's magnetic field? Or just...
No, so, well, Earth
No.
has a magnetic field, but this is another magnet. We're creating a magnet with a coil of wire.
Okay, yes.
I had some good visualizations in last Monday's class, that if you want to go back to those. But there was the rule that essentially, like, if we have a current flowing through a wire, the magnetic field goes around that wire, essentially creates concentric rings of magnetic field. So we have magnetic field lines that go around the wire like this. And so the third rule says not just a magnetic flux. So here we see that, like, we have some of these magnetic flux lines will pass through that coil, right? So, like, we're having magnetic flux lines kind of come around all like this, and some of them are going to pass through essentially behind that coil and then out and then kind of continually loop around. We see that? So we have these magnetic flux lines that are doing this, and so the third rule says not just that a magnetic flux through a coil produces current, it's that essentially the voltage around this coil is proportional to the voltage in this coil is proportional to the change in magnetic flux. So if the magnetic flux isn't changing, that's passing through this coil, then the light bulb won't light up. So if we keep this coil still, and we have a constant magnetic field here, due to the current, is this light bulb going to light up? No. Because there's a magnetic flux going through this coil, but it's not changing. Okay, now let's look over here. Same thing, except now our current is changing. If our current is changing, so I said, here we said if a current is passing through a wire, it creates a magnetic field. If the current is changing, what do we think is happening to the magnetic field? It's changing. So if the magnetic field is changing, so the magnitude of the magnetic field that's passing through, magnetic flux that's passing through this is changing. So in this case, we would light up here, right?
Wait, is this wire like connected to that circuit?
Nope, so this wire here, we can essentially think about this wire as just being connected to a battery.
And then that light bulb is just...
It's a completely separate circuit. They're not touching at all. Which is pretty wild, right? We can light up a light bulb without touching it.
I didn't understand.
I thought it was like a subset of.
Yeah.
Oh, you thought like this was like...
Yeah.
Yeah.
Okay. Sorry about that.
I was thinking of this question in terms of like Earth's magnetic field, but then I realized like that doesn't work in real life. You can't just like move something.
What's wild though is not the Earth's magnetic field, but if you take a big fluorescent light tube, like the ones that would be in those before they replace it with LEDs, those big glass tubes. If you take one of those and you go out to like rural Massachusetts or something like that, where they have those big power lines overhead, you can take that light bulb, carry it underneath those power lines, and that light bulb will light up. Yes. You can just hold the light bulb in your hand underneath the power lines and it'll light up.
And is that because it's
Because the big power lines above you are producing a magnetic field and what?
it's an alternating?
It's an alternating current. Those big power lines, these power outlets are all an alternating current, which means that the current is alternating, which means the magnetic field is alternating. And so if you have your big tube, it'll produce a voltage between the two ends of that tube.
Would that tube get hot?
As hot as it would normally be as if it was plugged in, but probably not even that hot. Sure, maybe. And then, yeah, if we were out in like UMass, if we're all the way out in what's that?
Wild West.
Yeah, in the wild west of Massachusetts. What's it? Starts with an A? Amherst, that's it, yeah. I once signed up for a conference, so like, I first moved to Boston, I'm like, oh, I'll go to a conference, like, it's at UMass, it can't be that far. I had to wake up at 6 o'clock to get there by the time the conference started. So here we have a alternating magnetic flux going through this coil, so the light bulb would light up. Alternating magnetic flux would produce a voltage in this coil, which would drive a current to light up the light bulb. Now we have a current flowing through a wire, and we're moving the coil parallel to the wire. Are we changing the amount of magnetic flux that's passing through this? No. So the magnetic flux changes. Does it increase or decrease the further away you get from the wire? It decreases. Decreases at an inverse rate. But because we're staying the same radius r away from the wire the whole time, the magnetic flux, there's still a magnetic flux passing through this, but it's not changing. Now the last one, we're constant current, so constant magnetic field, but we're moving closer and further away from the coil, or moving further and closer away from the wire. So what's happening there? We're going to light up again because the magnetic field as we move away is decreasing, and as we move closer, the magnetic field is increasing. So we have a changing magnetic flux because we're moving our coil. Glad I went over that. It seemed like that was helpful. Any questions? Anyone still feel a little lost? Go back and look at the notes from last Monday, and you'll hopefully see some nice photos or nice like diagrams that I think show the magnetic field lines around a moving charge, an entire wire, and if we put that wire into a coil.